Hello and welcome back. Today we're going to talk about projectile motion. In the past, we've looked at free fall. That kind of motion only takes into consideration the acceleration due to gravity. And that's because the motion is entirely vertical. With projectile motion, we'll be combining vertical and horizontal motion. So we're adding a whole new axis here. Let's say we've got a football player right here, and he throws a football up and to the right. Generally, what will the path look like for the ball? Well, it'll look something like this. That's a parabola. If you've thrown a ball or anything else at an angle, you can intuitively tell that the item will go up and then go down, but keep going in the horizontal direction you throw it. Pretty cool. Now, I mentioned that for projectile motion, we combine vertical and horizontal motion. We can analyze the two and combine our findings to gather details about the path the object traveled. Let's talk about horizontal motion for a second. In free fall, our vertical motion was dictated by a gravitational acceleration value. What kind of acceleration will be working on the object when it's moving horizontally? Now, you might be answering air resistance or drag, but when it comes to physics 1, we actually ignore those, which means there's no acceleration working horizontally. Taking all that in, we can realize that velocity in the x direction is constant. Acceleration is change in velocity, and in the horizontal direction there's no acceleration. So then velocity won't change. Horizontal acceleration is 0. Let's do a practice problem. Let's say that a football player is on a cliff. That football player kicks a ball perfectly horizontal at a speed of 20 meters per second. And the question is, after 5 seconds, how far will it drop? Now, this looks intimidating, so let's start with something easy. Roughly, let's draw the path that this ball is going to take. It's going to go down somewhere like that. It's roughly parabolic. Now, to start this problem, let's list what we know, but split it into x and y. Vx is the velocity in the x direction, and that is going to be positive 20 meters per second. It's positive because it's going right, and that is standard notation for positive. Vy is going to be 0 meters per second, because right off the bat, this ball is not moving vertically at all. It's being kicked completely horizontal. And I should mention that the two velocities I just wrote down are initial velocities. Now, what about acceleration? Well, acceleration due to y is going to be g, which is negative 9.81 meters per second squared. And we know that because g is the gravitational constant and is the only thing acting on the ball vertically. Acceleration in the x direction is going to be 0 because, like I said earlier, we're ignoring drag and air resistance. Those don't exist in physics 1. So there's nothing acting on the ball horizontally. So the acceleration in the x direction is going to be 0. We also know time equals 5 seconds, and that applies to both x and y, so I'll put it in the middle. We're looking for how far the ball will drop, so our result that we should get is a delta y. Let's look for an equation that we can use from our big three. Equation 1 doesn't have a delta y component, so I'm going to get rid of that. And equation 3 has a final velocity, which we're not actually interested in. So we're going to use equation 2. let's set this up. I'm going to change all of the x's into y's because we're asked for delta y. So delta y equals v naught t plus 1/2 a t squared. And you'll notice we're doing delta y, which means everything in this equation is going to be in terms of y. So this v naught is vy. This a is ay, because we're looking for a delta y. And v naught in the y direction is 0, so we can actually just get rid of this whole term. And we're left with delta y equals 1/2 ay negative 9.81 meters per second squared, t squared, 5 seconds squared. And you can take out your handy dandy calculator and find out that delta y equals negative 122.625 meters. That means the ball dropped 122.625 meters 5 seconds after the player kicked the ball. Now, you may have noticed that the x components are pretty useless in this problem. So let's do one where we actually use the horizontal direction. We'll use the same setup as before. But instead, let's say the cliff itself is 122.625 meters high. And based on our results on the last problem, that means the ball will reach the ground after 5 seconds. Now, the question is, what is the delta x of the ball? As in, how far horizontally did the ball travel after 5 seconds? Well, first, like I said, we know the ball is going to hit the ground after 5 seconds. So that's our t. From the previous problem, we can separate x and y components again. The only thing we're adding now is that delta y equals negative 122.625 meters. And we are looking for delta x. Let's try and use equation 2 one more time, this time in terms of x. So delta x equals v naught t plus 1/2 a t squared. And reminder, we're using x here, which means this is vx, this is ax. Now, ax is actually 0, so we can just get rid of this whole term, which leaves us with delta x equals v naught, which is 20 meters per second, times t, which we already found was 5 seconds, and that gives us a delta x of 100 meters. This means that the ball traveled 100 meters to the right after it was kicked. All right, that's your introduction to projectile motion. We'll be doing some more practice problems soon, so stay tuned and happy learning.